Today we're covering everything you need to master chemical equilibrium, writing K expressions, reverse reactions, the link to rates, temperature effects, Kp versus Kc, Q versus K, ICE tables, solving for equilibrium concentrations, and even understanding how systems respond to stresses. Let's get started. For a general reaction, A plus B gives C plus D. The equilibrium constant expression of K, also known as the mass action equation, can be written as the products over the reactants. So we'll say the concentration of C, so I put square brackets around the C, raised to the coefficient of C, times the concentration of D, raised to the coefficient of D, over the concentration of A, raised to the power of A, times concentration of B raised to B. So it's always products over reactants. An example of a homogeneous reaction is one where everything is like gases or aqueous. So an example will be like nitrogen gas plus 3 molecules of hydrogen gas to produce 2 ammonias, also gas. So the Kc will be equal to the products over the reactants. So the products will be the concentration of NH3 raised to the power of 2 over the concentration of N2 times the concentration of H2 raised to the third power. An example of a heterogeneous reaction is something like calcium carbonate, which is a solid, to produce calcium oxide and carbon dioxide as a gas. So here you have solids and gases all mixed together. Important rule is always ignore solids and liquids. They're not included. Okay, so if I'm writing my mass action equation, then I would say then that the Kc will be equal to concentration of CO2 raised to a power, so it's 1, so nothing's written there. What about ions? If I have an equation like copper solid plus 2 silver ions will produce Cu2 plus aqueous plus 2 silver solids. Again, I ignore the solids, so it'll be products over reactants. So it'll be Kc is equal to concentration of Cu2 plus over the concentration of Ag plus raised to the power of 2. Kp will use the partial pressure of gases. So P then will be equal to the pressure. So if I have an equation that says something like A plus B yields C, and all these are gases, then I can say that the Kp is going to equal the partial pressure of C raised to the power over the pressure of A raised to A times the pressure of B raised to the power of B. So otherwise, it's done exactly the same as Kc, except we're using pressures instead of concentrations. For reverse reactions, if you have a reverse reaction, you take reciprocal K. So if I had an equation like nitrogen plus 3 hydrogens giving me 2 NH3s, and suppose under these conditions, Kc is equal to 0.5. So then K prime is the reciprocal of this, so that will be equal to 1 over 0.5, which is 2. So simply stated then that K is equal to K forward divided by the K reverse. So equilibrium is really just a balance of speeds. All right, some important notes. If K is greater than 1, the forward reaction is favored. If K is less than 1, the reverse is favored. If K is equal to 1, then neither direction favored. Students often ask, well, what about catalysts? A catalyst do not change K. The catalyst only changes how fast the equilibrium is reached. It doesn't affect the K itself. Okay, why K depends on temperature. You probably already know that if I increase the temperature, it'll speed up a reaction. But which way? If it's an endothermic reaction, it speeds up the forward. If it's exothermic, then it will speed up the reverse. If you want it more mathematically stated, we can use the standard free energy equation. It's equal to negative RT, the natural log of the rate constant. So at standard conditions, this is our free energy. Okay, for R, we're going to be using 8.314. because we want to answer in joules. The T here will be the absolute temperature in Kelvin. All right, the natural log, and this is my rate constant or equilibrium constant. So remember, only temperature changes K, not concentration or pressure. Comparing between Kc and Kp, we have an equation that says that Kp is equal to Kc times RT raised to the change in N. Okay. For my R here, I'll be using the gas constant 0.0821. Temperature again is going to be in Kelvin. All right, this delta N, this is the change in the number of moles of gas. So essentially what you do is you take the sum of gas moles in their product and subtract the sum of gas moles in the reactant. If N equals 0, which means the same number of moles of gas in both sides, that means that Kp equals Kc. If delta N is greater than 0, that means that Kp will be larger than Kc. And if delta N is less than 0, then Kp is less than Kc. Okay, let's do an example here. All right, so if I have N2 plus 3 H2s okay, so let's look at my delta N. I have 2 moles here. I have 3 plus 1 is 4. That means that will be a negative 2. So my formula would be Kp is equal to Kc times 0.0821 times whatever temperature it is raised to the negative second power. Suppose I have 2 SO2 gas plus O2 gas to produce 2 SO3s gas. Okay, let's say if Kc is equal to 2.0, this is going to be at 500 Kelvin. Kp will equal 2.0 times 0.0821 times 500 raised to the power of, okay, so here I have 2 minus 3, so that's going to be a negative first power. So Kp is equal to 2.0 times 41.05 to the negative first power. So Kp would equal 0.049. All right, so what does K tell you about a reaction? Okay, we already said that if K is greater than 1, products are formed. If K is less than 1, reactants are favored. If K equals 1, it's a mixture of both. I'll change this instead of saying formed, favored. Should be better. All right, something to note. If K is greater than 10 to the third power, that means it goes very far to the right. It nears completion, in fact. Likewise, if K is less than 10 to the negative third, very little products are formed. So K essentially tells you how far a reaction goes. The thing about K is when the reaction is complete. Or at equilibrium, okay? Q is a measure at a point in time. An easy way to remember this concept is to write these in alphabetical order. I'll draw like a little bar graph here, where this one is K and this one is Q. If K is greater than Q, it's going to shift to the right. Likewise, if K is shorter than Q, the reaction is shifting to the left. If they're at the same height, then it's at equilibrium. Okay, ICE stands for initial, change, and equilibrium. So I'm going to create a table here. I'm going to write my equation here. Hydrogen, fluorine, and HF. I'm going to write it as 2HF. So in this first row, this is the initial concentration in moles per liter. All right, if you notice now, I have 3 moles here, 6 moles, in a 3-liter flask. Okay. So my initial concentration of hydrogen, I have 3 moles in 3 liters. So it's a 1 molar solution. My fluorine, I have 6 moles in a 3-liter solution. That gives me a 2 molar concentration. Initially, I have 0 hydrogen fluoride. Okay, as this reaction proceeds to the right here, I'm going to get less hydrogen. I'm going to have less fluorine, and I'm going to gain more hydrogen fluoride. I'm going to gain 2 times as much because it has a coefficient of 2 in front. All right, so at equilibrium, my concentration for hydrogen would be 1 minus X. For fluorine, it's going to be 2 minus X. And then for HF, it's going to be 2X. The problem says that my Kc value is going to be 1.15 times 10 to the positive 2. Okay. All right, let's set up our mass action equation then. Because I know in my mass action equation, I know that Kc equals my products raised to a power over my reactants. Raised to their powers. All right, so I'm going to say Kc, which is 1.15 times 10 to the second, is going to equal 2x squared. I got that from here. Over 1 minus x and 2 minus x. So if I work this out then, so 2x squared, that'd be 4x squared. Okay, so if I multiply here and here, and the same thing here and here, I would get 2 minus x minus 2x plus x squared equals, I'm going to go ahead and write this as 115. Okay, so let's clean this up a little bit. So that means I have 4x squared. And I want to rearrange this so it fits my eye better. So it'll be x squared minus 3x plus 2 equals 115. Okay, I need to cross multiply. So 4x squared is going to be 115 times x squared minus 3x plus 2. Let's set this up into quadratic format. So 0 equals 111x squared minus 345x plus 230. Okay, solving the quadratic, I will get x is equal to 0.968. So I will say 1 minus 0.968. That will give me 0.032 for hydrogen, be the concentration. 2 minus 0.968. I would get 1.032 for my fluorine. And 2 times 0.968. So I would have 1.936. So this would be my concentrations. Here we have another problem. Have a mixture of nitrogen monoxide and hydrogen to produce nitrogen and water. So I have the expression written out, and we know the initial concentrations. I have a water, but we have no nitrogen. But I know that at equilibrium, I have this number. So what we'll do is let's set up an ice table. Initially, I have 0.1 moles per liter. I have 0.05 moles per liter. I have no nitrogen. And I have 0.10 for water. And we're told that at equilibrium, I have 0.062 molar. So what let's do is, let's say 0.10 minus 0.062. That gives me 0.038. That's how much it changes. So this is going to be minus 0.038 because it's losing. My hydrogen is also going to be losing the same amount because it has the same coefficient in the balance equation. It'll be minus 0.038. The nitrogen has a coefficient of 1. So it's going to be gaining 0.038 halves. It's going to be gaining half as much as the others are losing. The water has the same coefficient of 2, so it's going to be gaining 0.038 also. All right, so if I subtract here, I will get 0.012 moles. If I divide here, I would get 0.019 molar. And this will be 0.138 molar. So that's the concentration of them. But it says calculate both the equilibrium constant also. So we got to do that. All right, so to get the equilibrium constant, that's going to equal the products over the reactants raised to a power. So this is going to be 0.19 raised to the first power. The water will be 0.138 raised to the second power. Right? The NO will be 0.062. raised to the second power and 0.012 raised to the second power. All right, so my Kc here will be 653.7, or we'll just round it to 654. That would be my Kc value. Okay, another ice box. I have hydrogen iodine forming hydrogen iodide. Initially, I have 0.20, 0.20, none here. I know that my Kc value is 49.5. Okay, I'm going to be losing X, and I'm gaining 2X. Okay, so we're going to say that Kc is going to equal 49.5 is equal to 2x squared over 0.2 minus x. Since both of these are 0.2 minus x, I'm just going to make this squared. To make the math a little easier, I'm just going to take the square root of everything. So the square root of 49.5 will be 7.04. That will equal 2x over 0.2 minus x. That way I don't have to do the quadratic equation. So if I cross multiply then, I will get 2x equals 1.41 minus 7.04 x. Combining like terms, I'll get 9.04x equals 1.41. And x will equal 0.156. Okay, so I'm going to say 0.2 minus 0.156. That will give me 0.044. Same for this one. And then 2 times 0.156. That will give me 0.312. All right, these are my equilibriums for my hydrogen iodide and hydrogen iodide. Let's talk briefly about the Chatelier's principle. This principle states that if a system at equilibrium is disturbed, it will shift to counteract that change that was applied to it. So if I were to add reactant, it's going to shift away from the reactant. So it's going to shift to the right. If I add products, it's going to shift to the left because I had to counteract that product that was added to it. If I increase pressure, it's going to shift to the side with fewer gas molecules. It's important now that you have to specify gas molecules there. If I increase temperature, if it's endothermic, it's going to shift right. Exothermic, it's going to shift left. Important note now, catalysts do not shift or change equilibrium. They just get you there faster. All right, so we're looking at this question at the bottom. It says here that it is endothermic, okay? So if it's endothermic here, what I normally do if I see that, on the left side, I just put plus heat here. Put plus heat on that left side. Okay. So if O2 is added, I'm going to go ahead and label these. This is my SO2s, my O2s, and I'm going to put SO3s over here. All right. So if I'm adding O2, okay, here's my yield sign here. So if I'm adding reactants, then what's going to happen is my O2 has increased. It has to shift to the right. So if it shifts to the right, then the SO2 must decrease and my SO3 must increase, because the reaction is going to the right. So I have to consume more SO2 and I will make more SO3. The second reaction is heated. Since this is endothermic, if I heat it, it's going to shift to the right. So if it goes to the right, then the SO2 has to decrease. The O2 must decrease, since it's going to the right. So therefore, the SO3 must increase. The volume of the reaction vessel is doubled. This is a 2, this is a 1, and this is a 2 here. 3 moles versus 2 moles. The volume of the reaction vessel is doubled. So if I'm doubling the volume, that means the pressure is decreased. Volume is inversely proportional to pressure. So if I increase the volume, the pressure must go down. All right. So if I decrease the pressure, it's going to shift to the side with the greatest gas molecules. All right. So I have on the left side, reactant side, I have 2 plus 1, which is 3 molecules. But on the right side, I only have 2. So it's going to have to shift this direction. So that means I'm going to increase the amount of oxygen. It's going to shift this way. And this is going to decrease because I'm shifting away from that side. Okay. Then the last one, it says I want to remove some SO3. So if I remove some, this goes down. Well, if I take something alpha here, everything's got to shift to the right to fill in what was taken away. So it's going to shift to the right, thereby decreasing and decreasing. Okay, that's a quick explanation of the Chatelier's principle. Okay, in this problem, we're going to be measuring the concentration at some point in time. So it says, let's suppose at some point in time, which means then that we're doing Q instead of K. So same formula, Q is equal to concentration of the HI, which is the product, squared, because this is hydrogen plus iodine gives 2 HIs. Okay, so we have 0.5 HIs. And we're going to square that. The H2 is 1 times 10 to the negative 2, so that's 0.01. And then the iodine is 5 times 10 to the negative third, so Q is equal to 5,000. The problem says that K equals 100. So Q is greater than K. If Q is greater than K, it's going to shift to the left or reverse, okay? All right. So let's go ahead and set up our ice table. This will be done a little differently since it's going in the opposite direction. All right, so initially, so this will be 0.01, 0.005, and this is 0.5. All right, we're going in this direction. So therefore, I'm going to lose 2x. I'm going to gain an x, and I'm going to gain an x here, like this. That makes this side 0.01 plus x, 0.005 plus x, 0.5 minus 2x. So setting up our mass action equation then, I'd have 100 equals 0.5 minus 2x squared over 0.01 plus x times 0.005 plus x. I'm going to use my numeric solver on my calculator to solve this because quite a bit of algebra involved and we're kind of running out of time. So putting it to my numeric solver on my TI-84 calculator, set my x to 0. I need to reseed the x, and I come up with x is equal to 0.0355. That means that this is 0.01 plus 0.0355. This one is 0.005 plus 0.0355. And this one is 0.5 minus 2 times 0.0355. So that'll give me, we'll write them here. The H2 concentration then will be 0.0455 atmospheres. I2 will be 0.0405 atmospheres. And my HI will be 0.429 atmospheres. Okay, and that will be my answers. So today you learned how to write K expressions, predict reaction direction using Q, solve equilibrium problems using ice tables, and apply the Chatelier's principle. Mastering equilibrium is a huge step in chemistry. It connects kinetics, thermodynamics, and real-world reactions. If this helped you, make sure to like and subscribe for more chemistry. If you want to practice problems on a worksheet or a PowerPoint, check out the link in the description. And I'll see you in the next lesson. Goodbye.